So here we have an example of a determinate truss, or one that we'll assess for determinacy and stability in a moment. We're asked to check and see if it is determinate and stable, and to solve for all member forces. And this particular truss is quite a common configuration that we might see in, say, bridges or in some commercial structures. And what we'll see in this truss is there are quite a few zero force members. So I think our first task should be identify those zero force members. And if we recall that we have two rules we've identified for finding zero force members. So first, let's just write down what we'll do. Let's find our zero force members. And we want to do that as our first step in any process because it simplifies the truss down to something that's a little bit more reasonable for us to solve. So if we recall from class, we had case 1. And in this case, we had two members framing in to each other. So here we have force due to member 1 and force due to member 2. They frame into each other and they're not collinear. So two members at an angle. And there's also no force or reaction at that joint. And in this case, we can say that both members are zero force. And in class we saw why, but it's really a quick thing to understand. If we take equilibrium, we have a y component here and we don't really have one there. We just can't satisfy equilibrium with having only two forces framing in at different angles. For case 2, we identified where we had a joint and three members framing in. And in this case, we had these three members, two of which were collinear. In other words, they are going in the same direction. Here we have the member 2 and the member 1 going in the same direction. And no external force or reaction. And if that was the case, we could say that the non-collinear member is zero force. So in this example, we could go through and we could say that this is a zero force member and both of these are zero force members. So that means we can apply those two rules, those two cases, general cases, to our truss above and see if we can identify some members that we don't need to consider in our analysis. And this will make us our analysis a lot simpler. So if we build ourselves a little table with joint and then member and then case as provided above. And first let's start at joint B. And at this joint we can see we have two non-collinear members framing in with no external force. So that means that both members BA and BD are zero because of case 1. And we can go here and we could identify that there's zero right on our diagram. We could apply the same logic at joint J and see members JH and JI from case 1 are both zero force members. Now we don't have any more case 1 instances in this problem, but if we look at joint C, we can see we have case 2. In this case we have member CD is a zero force member in case 2. We have the same thing at joint F, 3 members, 2 of which are collinear and 1 is not, and no force. That means member FE is 0 force. At joint G we have 1, 2, 3 members, the same thing happening. So we have 0 force members on these internal vertical chords. So at joint C we've already labeled that, and then we can put in joint F, and then member FE, case 2, and joint G, member GH, also case 2. Now we've identified several 0 force members and simplified our problem considerably. And when we go to analyze this truss, we can redraw it without those 0 force members being in the way. And we'll see now that we have a much, much simpler problem. So let's do that. Let's redraw our structure, accounting for the 0 force members. So if we start, let's say here, then we're going to go over a total of 12 meters. And up a total of 4 meters. And we see that we're already considerably simpler of a truss without those end members. We've got a pin-ended connection and a roller. We do have a joint here and here and here, and we've got a force here of 12 and a force here of 8. Those are our externally applied forces. And then we can label our joints as well, just since we can refer to this diagram while we're solving rather than the more complicated one. So these are the total number of joints that we're interested in now. You'll see we still have several joints that we need to solve for. However, some of these joints, such as C, F, and G, will be able to quite simply state the force in the left-hand side of the joint is equal to the force in the right-hand side. We'll see that mathematically when we look at joint C, and then we'll just apply that condition to the other joints. So really, what we're going to look at here is solving 1, 2, 3, 4, 5 joints in this truss. And this truss started off considerably more difficult. Now let's go to the stability and determinacy aspect of this. And technically, I guess we should have done this before we did the 0 force members, because if it's not stable and if it's not determinate, then we can't solve it, so we should just stop at that point. It is solvable if it's indeterminate. It's just not solvable with the method of joints that we're using for this problem. So just a note here that stability and determinacy are both assessed with the original structure. In other words, the one prior to that, identifying all those 0 force members. So we're going to assess this structure here for stability and determinacy. So let's look at this. What we need to do here, first, if we're going to begin with determinacy, we know that SI is equal to B plus R minus 2J. And B is equal to the number of members in our original truss. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And R is the number of reactions. We have a pin that gives us 2 reactions, or I should point at this one. A pin has a reaction in the X and a reaction in the Y. And a roller has 1 reaction in the Y. It gives us 3 reactions. And then the number of joints, J, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we do this calculation for SI, which is the degree of static indeterminacy, we can see we have 17 plus 3 minus 2 times 10. And SI is equal to 0. And that means that we have a determinate structure. And if it's determinate, it means that we can solve this truss using the method of joints. We can solve it with equilibrium conditions only. We don't need to bring in some more advanced stuff from future courses. Stability is also assessed generally at the same time as determinacy. And here we're looking at some of the rules we have. First off, SI is greater or equal to 0. So we have enough supports for it to be stable. And then our reactions. There we have AY going up, AX going to the left, and IY going up. So they're not all parallel, because AX is not parallel to the other 2 reactions, and they're not all concurrent. They don't all intersect with the same, or at the same point. So that stability condition is met. And then our next condition simply is no internal collapse mechanism. And this is something that we can sort of say by observation, but let's look at what we mean by that. Coming back to our original structure, we have a series of simple trusses. A simple truss is a triangular element. A triangular element, 3 members that form together to form a triangle, is by its nature stable. So if we have a stable section here, a stable here, 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 all the way through the truss, we have a total stable truss. If we had a section that didn't have one of these diagonal chords, well then we're introducing this internal collapse mechanism and stability is not retained. So stability is a little bit more complicated than that, internal stability, and it takes a little bit of experience to totally identify every case that is not stable or every case that is stable. It has a lot to do with your support conditions and the geometry of the internal structure. But here we're looking for obvious flags, and we don't see any obvious instability problems for the internal structure. So stability is retained, and it is determinate. That means we can go ahead and solve this. So let's look at our reactions first. And to do that, we'll draw a free body diagram of the truss that's simplified down just to the bare minimum information we need in order to solve for our reactions. So here is the outline of the truss. We might as well put in the diagonals as well. Doesn't hurt. And then we know that at joint A, we will have AY, we will have AX. At joint H, we have 12 and 8. And at joint I, we will have IY alone. Since it's a pin condition, it only provides one reaction, or a roller condition at IY. And let's give some measurements here. We have distances here of 3 meters, 9 meters. And finally, a vertical distance we'll need of 4 meters. So that's enough information to solve for IX, or IY, AX, and AY. Now, we also started with reactions in this problem, unlike other problems that we might start with the joints first, because we only have 3 reactions. If we have 3 reactions and 3 equations of equilibrium, it's very simple for us to immediately solve for those reactions with sum of forces in X, Y, and sum of moments. So let's apply equilibrium to this problem and solve for our reactions. Now, equilibrium for this rigid body is the 3 equations that I just mentioned. Since we do have distances between the forces, we can bring in our moment equilibrium as well. If we take sum of forces in X and set that equal to 0, we can say that AX plus 8 is equal to 0. So this X force plus that 8 force is the only forces in the X direction. This is in kilonewtons. And this gives us AX is equal to minus 8 kilonewtons. That means it's going in this direction here, the opposite direction to what we've drawn it, or to how we've drawn it. So we draw it positive according to our sign convention, and if it comes out of our equation as negative, that means it's opposite to how we've drawn it. Now we can put in our sum of moment equation. If we jump right to sum of forces in Y, well, we have 2 unknowns in Y and we can't directly solve for it. But if we take sum of moments about point A or point I, then we'll remove one of our unknowns because they will pass through the point about which we're taking moments. So let's take sum of moments about point A and call that 0. That means that we have 2 or 3 forces contributing to the moment. We have IY times 12 meters, and this is rotating counterclockwise, which is positive. To that, we're subtracting 12 kilonewtons times 9 meters, which is rotating it clockwise, it's negative, and we're subtracting 8 kilonewtons times 4 meters, rotating it clockwise, and setting that equal to 0. This allows us to solve for IY is equal to positive 11.667 kilonewtons, which is, since it's positive, it's going in the direction we drew it, which is up. And we can say that sum of forces in Y is equal to 0, our third equilibrium condition. Alternately, we could take sum of moments about point I and set that equal to 0 and solve for AY. And we can say that AY plus IY minus 12 is equal to 0. Since we just solved for IY, we can plug that value in. AY is equal to 12 minus 11.667 is equal to AY of 0.333 kilonewtons up. So now that we've found our reaction values, all 3 of those, we need to start working on our joints. We need to identify a joint that has 2 or fewer unknowns. And I can see that there's 2 joints with 2 or fewer unknowns that we could start with. We could start with joint A or joint I. Joint I has unknowns in this direction and this direction, and A has it here and here. I chose joint A to start with, but it doesn't matter which one you choose. Our first step, once we've identified the joint with 2 or fewer unknowns, is to draw in our free body diagram and what we call the local coordinate system. Remember, we had a global coordinate system that deals with x and y generally, horizontal and vertical. And we have a local coordinate system that deals with forces along the length of the members for trusses. So here we're putting in our known values. We have a known value of AX is equal to 8 kilonewtons. And since we calculated it going to the left, we'll put it in going to the left. And we have a known value of AY is equal to 0.333 kilonewtons. And that's going up. We know something about the angle of this chord. It happens to be at a 3, 4, 5 triangle. Let's look back at our original geometry really quickly and verify that. We have 3 meters over. We have 4 meters up. That means that this diagonal length is 5. A 3, 4, 5 triangle. Now that we have that established, we can say that we have an unknown. This is joint A down there. We have an unknown acting along the length of the member in positive local coordinates, meaning tension is positive, FAD. Force in member AD. Here is, let's bring this diagram into play here. Here's joint D. So we're dealing with a force in member AD, and we label it the joint that we're sitting on and the joint that we're looking at. So A is where we're sitting and D is where we're looking. And then since we don't know this value, this is FAC, we'll draw it as positive as well. To that, we can now go ahead and draw, well, we can say a couple things. We can say that FADX, the x component of FAD, is simply equal to 3 over 5 times FAD. It's the similar triangles associated with the slope of this, or with the angle of this chord. And FADY is equal to 4/5 FAD. So let's just get that out of the way. Now that we have that, we can now go ahead and draw this in what we call the XY coordinate system, or Cartesian coordinate system, or global coordinates. It makes it a little bit simpler for us to apply equilibrium. We have an unknown force going up of FADY, the y component of FAD. So this is equal to 4/5 FAD. We have an unknown force going this way. The x component of FAD is equal to 3/5 FAD. And we note that if FAD is going up and to the right, then FADX, the x component of that, has to be going to the right, and the y component has to be going up. The x component, if the x component was to go to the left, the y component would have to go down. The force vector, if we do the vector sum of these two components, has to follow the slope or the angle of that chord. So we know that FAD is going to the right and FADX is going to the right and FADY is going up, based on how we drew FAD. Here's the key point to solving the method of joints, is to draw our diagram in the local system with all of our unknowns acting in the positive coordinate or positive local direction. Tension force here, tension force there, and all of the knowns acting in the actual direction that they're acting. So we have AY going up and AX going to the left. When we break this down into our global coordinate system, we apply the forces, component forces, in this direction that is based on how we drew it in the local system. So these are going to the right and going up, because FAD was going to the right and going up. And then when we go ahead later and take equilibrium of this local system, if things come out to be positive, that means we drew this correctly. If they come out to be negative, that means that this has to be flipped. So once we are comfortable drawing this, and then draw this so that it reflects the actual directions that are coming from that coordinate system, we can begin to trust our results. And trusting the values that come out of our equations is imperative when we do these calculations, because Otherwise, we'll have no idea if the force is a tension or a compression force, and it can become quite cumbersome to solve these problems. So once again, they're all going in the direction according to this diagram. So now we can see that we have two unknowns, and we have two equations to solve those unknowns. We have the sum of forces in x and the sum of forces in y. So let's apply equilibrium and solve this. We can say that the sum of forces in x is equal to 0, and the sum of forces in y is equal to 0. So this is our equilibrium of a joint. And this is the goal of this method, is to get to the point where we can draw a free body diagram for that joint and solve for equilibrium. Okay, so let's go ahead and do that. If we take sum of forces in x right away, we'd see that we have FAC and FAD in 8. We have two unknowns in the x direction, so we can't directly solve for an x value. If we take equilibrium into y, we have FAD and 0.33. That means we can solve for FAD immediately if we take equilibrium in the y direction first. So sum of forces in y is equal to 0. This gives us plus 4 over 5 FAD plus 0.333. They're plus because they're going up. Recall that here's x, here's y, here's theta. This is our positive coordinate system in our global system. And that's equal to 0. Now we can say that FAD is equal to minus 0.4167 kilonewtons. This means FAD is equal to 0.4167 kilonewtons in compression. So y minus and y in compression, well, we drew FAD as a tension force. It came out as negative in our calculation, and our calculation was based on this diagram. It was based on this one. So it all flows, and we get a negative value, and that means this has to be flipped, and it's a compression force, not a tension force. So we can say it's compression because it came out negative. Now if we apply equilibrium in the x direction, we can get FAC plus 3 over 5 FAD minus 8 is equal to 0. So FAD turned out to be a negative number, but we're going to say this plus FAD because we're working on how we drew this diagram. So we drew this diagram going this way. When we plug in the value of FAD, it will be minus. So we have FAC plus 3 over 5 times minus 0.4167 minus 8 is equal to 0. And this gives FAC is equal to plus 8.25 kilonewtons in tension. So at that point, we can draw our free body diagram for that joint, showing exactly what's happening there. We're going to have some forces here, and we have a compression force, FAD is equal to 0.4167 in compression. A tension force, FAC is equal to 8.25 in tension. A vertical reaction, AY is 0.333 kilonewtons up. A horizontal reaction, AX, is equal to 8 kilonewtons to the left. And this would be our summary diagram for that joint. And if we look at it, everything is in equilibrium. We have 8 to the left, 8.25 to the right, and a small component of this 0.4167 to the left. That plus the x component here add to 8.25. And we can use the same logic in the y direction. So now we're ready to move on to another joint. Another joint where we have 2 or fewer unknowns. And in this case, that would be either joint C, joint D, or joint I. So let's look at joint C. Let me just show the diagram again where that joint C is. Joint C is here. We found the force in member AC. Now we need to find the force in member CE. This is a rather trivial calculation. We'll go ahead and do it one time anyway. If we draw that member, there's our joint. We said that we had a tension force in FCA or FC is equal to 8.25 kilonewtons. And then we have an unknown force, FCE, in tension. And we can put sum of forces in X is equal to 0. So FCE minus 8.25 is equal to 0. That means that FCE is equal to plus 8.25 kilonewtons in tension. So that was relatively trivial. We could get that by inspection or by observation. So let's go ahead and do that for the remainder of the joints like that in this structure. If we look at our diagram here, we can say that we have joint. We have the left-hand side of that joint and the right-hand side. So we can say that if we had joint, which we just did, joint C, the left-hand side is FCA, and this is equal to FCE. If we had joint F, the left-hand, F up here, the left-hand side is FD, and that's equal to FH. And then joint G, we have FGE, and that's equal to FGI. So we don't know some of those values yet, but we know enough to not have to do the calculations at those individual joints anymore. So now let's move on to a different joint, and we'll choose joint D now. So we know we have 2 unknowns here. We know the force in AD. We don't know the force in DE or DF. Our other joint with 2 unknowns is joint I. We could have gone to that instead. So at joint D, we're going to first draw our free body diagram of the joint in the local coordinate system. And this is D here. And we know something. We know we have a force here. FDA is equal to FAD, which was 0.4167 kilonewtons. And we don't know this value, FDE, yet. And we don't have any idea what FDF is yet. So we'll draw them as positive in our local coordinate system, which is tension. We do know something about these angles. We have a 3, 4, 5 triangle there, and we have a 3, 4, 5 triangle there. So we can say that FDAX, the x component of FDA, is equal to 3 over 5 FDA, and this is equal to 0.25 kilonewtons, and FDA y is equal to 4/5 FDA, and that's equal to 0.333 kilonewtons. And we can say that FDEX is equal to 3 over 5 FDE. So the x component of this force is 3 over 5 times its value, and FDEY is equal to 4/5 FDE. So once we know those values, we can plug them into our diagram for the joint in the global coordinate system. So let's draw that here, and we can say that here is our joint. To that joint we have FDF already acting in the x direction alone, so we don't need to worry about finding coordinates for that. We have a force going up, and this is the y component of FDA, so it's 4/3 FDA is 0.333. We have a force acting this way, and that is 0.25. So that's x component of FDA. And we have forces that are pulling us down. This is 4/5 FDE, and a force that's pulling it over. This is 3/5 FDE. And once again, these forces are drawn in such a way that they match the vectors that have to be there based on the direction of the chords and our assumption of positive tension force in our unknowns or our known force direction. We have that value, so we can begin to take our equilibrium at that joint. We say sum of forces in y is equal to 0. We'll start with that because we only have one unknown in the y direction. And we can say that 0.333 minus 4 over 5 FDE is equal to 0. That gives us FDE is equal to plus 0.41667 kilonewtons, which is a tension force in that chord. Now that we know FDE, we're able to solve for FDF, our other unknown value. Let's take sum of forces in x is equal to 0. And here we can say that 0.25 plus 3 over 5 times FDE plus FDF is all equal to 0. And this gives us FDF is equal to minus 0.5 kilonewtons. That means that FDF is equal to 0.5 kilonewtons in compression. So, why compression? Because we drew it in tension originally, and it came out as a negative value, meaning that it is going in the opposite direction, so it's compression. Finally, let's draw our summary for that joint. We have some forces acting on these chords that we just calculated. So we have a compression force here of 0.5 kilonewtons is equal to FDF. We have a force here that is tension. FDE is equal to 0.41667 kilonewtons. And we have a force over here, FDA is equal to 0.4167 kilonewtons. And we can say that this is a compression force, this is a tension force, and this is a compression force. And that's our summary for joint D. At this point, we're ready to move on to another joint in our diagram. So let's have a look at where we could go. We know all of the forces in member D, or joint D. That means we know DF. And by knowing DF, we know FH. We know DE, we know DA, we know AC. By knowing AC, we know CE. So if we go to joint E, we only have two unknowns. If we go to joint H, we only have two unknowns. And if we go to joint I, we only have two unknowns. That means the choice is ours where we go at this point. I chose to work on joint E next. We're on page 5 here. So for joint E, we can begin, as always, with drawing our free body diagram in the local system. Draw on our chords. We'll draw in our forces acting off of these chords. So we know that we have a value of FAC is equal to 8.25 kilonewtons here. We have a value of FEG, the force in member EG. We don't know the magnitude, it's an unknown, so we're drawing it as tension positive. We have FEH, that's also an unknown, so we're going to draw it going tension positive. We have FED is equal to 0.4167 kilonewtons in tension. We drew it as in tension because that's what we calculated before. We know some stuff here. We've got a 3, 4, 5 triangle. You see that all over the place here in this problem. On both of those chords we have that. And once again we can find the components of the inclined forces, components in the x and the y direction. So FEDX is equal to 3/5. FED is equal to 0.25 kilonewtons. And FEDY is equal to 4/5. FED is equal to 0.333 kilonewtons. We also know that FEH x is equal to 3/5 FEH, and FEH y is equal to 4/5 FEH, due to the geometry of this inclination of that chord. Knowing that, we can go to the next little bit here and draw the global free body diagram of that joint in our Cartesian coordinate system. So here's joint E. And let's start to apply some forces here. We know we've got 8.25 going that way. FEDX has to go in the left and FEDY has to go up. So we've got an x force component here of 0.25. That's FEDX that we calculated there. We've got a y force component of 0.333. And then we've got some unknown forces in member EH. We've got a 4/5 FEH, and we've got a 3/5 FEH. That's the x component and the y component of FEH. We know their directions to the right and up based on the direction of FEH. And we've got one more force here. We've got force FEG. That's already in the x component completely, so we don't need to get xy components for that. At this point, our next step is to apply equilibrium. So we'll apply sum of forces in x and y. Once again, if we apply sum of forces in y first, we can directly solve for a value. So let's do that first. This means that we have plus 0.333 plus 4 over 5 FEH is equal to 0. It gives us FEH is equal to negative 0.4167 kilonewtons, which is FEH is equal to 0.4167 kilonewtons in compression. We know that because it comes out as a negative value, and we've been following our sign conventions as we did this problem. Now let's solve for FEG. To do that, we'll come over here and we'll take sum of forces in x is equal to 0. And that gives us FEG plus 3 over 5 FEH minus 0.25 minus 8.25 is equal to 0. So this going plus, minus that, because of our sign convention. Let's plug in some values. FEG plus 3 over 5 times minus 0.4167. We just calculated it here. Minus 0.25 and minus 8.25 is equal to 0. And we can now say that FEG is equal to plus 8.75 kilonewtons. If it's plus, it means it's in tension because we've been following our sign convention. And we can draw our summary diagram for the forces in the members framing into that joint. So we've got FAC, or sorry, this is not FAC, that would be, no, okay. We've been calling it FAC all this time. Let's clear some stuff up on that though. We're at joint E now. I've been calling it FAC that we've calculated over there. That was an omission on my part for not changing the name. We then went to joint C and changed the name from FAC to FCE, and now if we're at joint E, we can call it FEC. So really this FAC is also FEC, and this is also FEC is equal to the values that we just calculated. So FEC is equal to 8.25 kilonewtons in tension. And then here we have FEG is equal to 8.75 kilonewtons in tension. We have, this is joint E down here. We have FEH, which was negative. That means it's a compression force here. FEH is equal to 0.4167 kilonewtons in compression. And here we have the force FED is equal to 0.4167 kilonewtons in tension. So let's just separate some of our stuff here so that it's a little easier to see this drawing. And that's the summary diagram for joint E. Now let's look at our problem and see what we don't know and what we do know. At this point we've done joint A, D, E. We know joint C, joint F, and joint E, or joint G. That means that joint H and joint I haven't been solved yet. And if we look at joint H here, we have known quantity in EH, known quantity in FH. We don't know what's happening in HI. If we look at joint I, we know what's happening in GI, but we don't know what's happening in IH. So either one is about as difficult as the other. At joint I, we also know the reaction. It doesn't matter which one we choose. I happen to choose joint H. So we'll go ahead with that joint in this case. To do this, we will begin with drawing our free body diagram in our local coordinate system. Now this joint seems like it has a lot going on, but really it's not that much more complicated than the others. Just we have these external forces happening at this joint. So we have 12 kilonewtons and we have 8 kilonewtons. And then we have some stuff happening here. We've got a force in this member, F H F is equal to 0.5 kilonewtons from what we solved before for joint D, when we found DF, and then at joint F we could say that it's equal to force FH, and now we can be at joint H and looking at F, and we can say that that is equal to force HF. In this member here we have force HE is equal to 0.4167, and here we have an unknown quantity, so we're going to draw it as tension, and this is force HI. To that we'll add some known information on our geometry here. We have 3, 4, 5 triangles. And we can say, like we've done before, that we have relationships for F, the X and Y components of FHI and FHE. So FHE X is equal to 3 over 5 FHE, and this happens to equal to 0.25. FHE Y is equal to 4/5 FHE, and that is equal to 0.333 kilonewtons. And FHI X is equal to 3 over 5 FHI, and FHI Y is equal to 4 over 5 FHI. So now we can go ahead and draw our free body diagram in the global coordinate system, and I believe I have room to do that, say somewhere right about here. So we've got some known quantities framing in here. We've got a force, 12. We've got a force over here of 8, pulling it away. We've got a force pulling it down, FHIY, of 4 over 5 FHI. We've got a force pulling it over here of 3 over 5 FHI. And once again, they're going in the direction that would add together to form that vector. And then we've also got forces acting at this joint, 0.25. That's this value, FHEX, and a value here of 0.333. That's that value, FHEY. And finally, we've got force FH. FHF framing into that joint. FHF is equal to 0.5 kilonewtons. So that's our free body diagram for the joint in our Cartesian coordinate system, our global coordinates. We can go ahead now and apply equilibrium and solve for our unknown value FHI. Since it's only one unknown, we really only need one equation of equilibrium. So let's take, if we take sum of forces in y, we could get it right away. Or if we take sum of forces in x, we could get it right away. Either one works, so I took sum of forces in x and set that equal to 0. And here we have 0.5, this force, plus 0.25, plus 8, plus 3 over 5 FHI is equal to 0. This gave us FHI is equal to minus 14.583 kilonewtons, and FHI is equal to 14.583 kilonewtons in compression. Now we'll note that this value is considerably higher than any of the other forces we've been calculating, and it's because it's taking the brunt of the load from this 12 kilonewton force and that 8 kilonewton force. So our other diagonal forces were 0.4167 kilonewtons, and now we're 14.583 kilonewtons on that force. So now we've solved for that value, and we can go ahead and draw our summary joint. Note that if we wanted to solve, well, let's check this. So let's check with sum of forces and y is equal to 0, and we can say that 0.333 minus 12 minus 4 over 5 FHI is equal to 0, and then we could find that FHI is equal to minus 14.583. So either one would work, and we could use that as a check. We can draw our summary joint now, or summary of that joint. So we've got a cord going this way with a force, the cord coming down here with a force, cord coming down here with a force, our external load in two directions. That's 8, that is 12. Framing into this, we have FHF is equal to 0.5 in compression. We have FHE is equal to 0.4167 in compression. We have FHI is equal to 14.583 in compression, and our external forces. Now we're ready to look at our problem again, and let's see what we know and what we don't know. If we go back and look at our structure, as we've identified we need to solve it, we've worked on joint A, joint D, joint E, and joint H. We also found the reactions. That allowed us to solve all of the member forces coming off of A. The member force at C we knew on either side, and F we knew on either side, and G we knew on either side. If we add up everything we know here, we find that we know every single quantity of this truss already. We don't need joint I. That being said, we will use joint I as a check. So we now know every force. So let's check our work. And we'll check with joint I. If we can find that joint I is in equilibrium using the numbers that we just found, we know that we didn't make any mistakes. If it's not in equilibrium, we know that we have some issues and we'll have to go back and figure out what went wrong. So let's check with joint I. Step number 1 is always to draw the free body diagram of that joint in a local coordinate system. So we've got joint I here. And we've got some members framing into it. We've got a vertical reaction. So IY is equal to 11.667 kilonewtons. FIH is equal to 14.583 kilonewtons. FIG is equal to 8.75 kilonewtons. And if we were to go ahead and, well, first let's give ourselves a 3, 4, 5 triangle here. And we can say up, let's go up here and I'll just write it there, that FIHX is equal to 3 over 5 FIH. And this happens to equal to 8.75. And FIHY is equal to 4 over 5 FIH, and that's equal to 11.667. So now we can say that this drawn in our global coordinate system, there's joint I. We have a reaction IY. We have a vertical reaction here of vertical force of FIHY is equal to 11.667. We have a horizontal force here of FIG is equal to 8.75, and we have a horizontal force here of FIHX is equal to 8.75. Now we can trivial calculation, but we should do it nonetheless. Sum of forces in X is equal to 0. We can say 8.75 minus 8.75 is equal to 0. Sum of forces in Y is equal to 0. We can say 11.667 minus 11.667 is equal to 0. That means that we are okay. We didn't make a mistake. So we have only one outstanding requirement left, and that's to draw our summary diagram. And our summary diagram tells us an awful lot about what's happening in this truss at a quick glance, so we don't have to look back at our 6 pages of work. This summary diagram contains our original structure and all of our joints. On that structure, we draw our forces in tension or compression. Now I've identified compression as red, and I'm going to use the convention where we put brackets around a compression force, and tension is going to be written in green, and there's going to be no brackets. Zero force members will consist of black with a circle through it, so we can go through, and we've identified these zero force members earlier on. Let's cross them out right away here. Now let's go ahead and draw in our member forces. Well, first let's start with our reactions. AX, and this is equal to 8 kilonewtons going to the left, and AY is equal to 0.333 kilonewtons going up, and IY is 11.667 kilonewtons going up. Now if we draw in our compression forces, that means we've got arrows compressing the cord, and in between that we'll write our force, 0.4167, and we'll write the other compression cord over here. We've got the same value, 0.4167. Arrows are compressing that cord. Here we've got another compression cord. There we've got 14.583 in compression. Up top we've got a compression cord here of 0.5, and here we've got a compression cord of 0.5, and then we'll draw our tension cords. Tension cords are stretching the member out, so here we have 0.4167, and we have tension along the bottom of this truss, 8.25, 8.25, 8.75, and 8.75. And at this point we're done with the analysis of the truss, and we've reported our solution as a nice neat drawing with our member forces drawn on top of the members, clearly identified as compression or tension. We have backup identification marks with our arrows on our cords. We have our reaction shown, we have all of our joints loaded, or our joints shown, and we have our external loads shown on the diagram. And at that point we're ready to end the problem.